If you recall, this was the last example that we have seen. So essentially, this example shows that if there is degeneracy in the problem, in a given LP problem, then the simplex method may run into some difficulties. And just to sort of recall this example, so we have this LP problem. So this is our starting Tableau. And then what we do is we sort of do a bunch of simplex iterations. So, we basically enter certain variables and certain variables leave the basis. And the problem was that essentially after doing a sort of number of steps, we actually come back to the same Tableau that we started with, right? So, and we said that this is a problem because essentially, we do a number of iterations and we sort of, get back to where we started, okay? So we don't make any progress at all. And this is known as cycling. And this happens when there's degeneracy in the problem. So first of all, I want to give you some remarks. So if no care is taken in choosing the entering or the leaving variable, the simplex method may cycle over a finite number of degenerate basic feasible solutions and return to the first one. So remember, this was precisely the problem that we sort of diagnosed on this example. And again, the problem actually arises from the following. So the same corner point can be represented by a different choice of basic variables, as a result of which, even though we change the basic variables, we're not really making any progress, okay? We're still looking at the same corner point. And in this example, there are at least 6 different representations of the same corner point, okay? 6 different representations of the same corner point using different basic variables. So as a result, we arrive at the same Tableau that we started with. And as we said last time, this is not good, right? So essentially, we make a bunch of steps, but in essence, we don't make any progress at all, okay? So this is known as cycling. In such a case, the values of all variables including the objective function value, remain unchanged but only basic and non-basic variables change. So this was an observation that we made last time, if you recall. So if I look at any one of these simplex tableaus, what I do see is that, only x7 is equal to 1 in all of these solutions, and all the other variables are equal to 0. The only change is that some variables become basic and some of them become non-basic. Okay, so only the set of basic and non-basic variables change, but the values of the variables are the same, including the objective function value. Okay, the objective function value is equal to 0 in all of these solutions. And if you think about this a little bit, this makes perfect sense because we're not really moving, right? So we're still looking at the same solution, as a result of which, obviously, the objective function value does not change, okay? And neither does the value of any other variables, okay? The only difference is that the labels of variables are changing, okay? So some of them become basic and they become non-basic and so on and so forth. But if you look at the right-hand side values, only x7 is equal to 1 and every other variable is equal to 0, basically, okay? So the question is, how can we avoid it? So is there a way to sort of overcome this difficulty? And the answer is yes. So this is known as Bland's rule. And here is what the rule says. So at a degenerate tableau, at a degenerate simplex tableau, among all choices of entering variables, among all choices of entering variables, choose the one with the smallest index. I'm going to explain what this means in a minute. And among all basic variables achieving the minimum ratio, among all basic variables achieving the same minimum ratio, choose the one with the smallest index is the leaving variable. Now let me give you a minute to sort of write this down. So essentially, if you think about this a little bit, so what Bland's rule tells me is how to pick entering and leaving variables, basically, okay? So whenever I have a degenerate basic feasible solution, it gives me a rule that I can apply when I choose the entering and leaving variables. So it says the following. If there's more than one choice of entering variable, okay, so which means that for a maximization problem, if there's more than one non-basic variable with a negative coefficient in row 0, right, so they are the candidates for entering variable, I'm going to pick the one with the smallest index. What does that mean? So for example, I'm going to give you an example here, but if x1 and x5 are potential candidates for the entering variable, then 1 is smaller than 5, okay? The index of x1 is equal to 1, and the index of x5 is equal to 5. And since 1 is smaller than 5, I'm going to actually pick x1, okay? And similarly, so it says among all basic variables achieving the same minimum ratio, what does that mean? So in such a case, of course, there's more than one candidate to leave the basis, right? So we have seen this before. So if there's more than one basic variable achieving the same minimum ratio, then any one of them can leave, basically. So what we're going to do is we're going to apply the same rule. I'm going to choose the one with the smallest index, so which means that, for example, x2 actually would be preferred over x4, okay, since 2 is smaller than 4. Okay? Let me illustrate this on this example. So this is the starting solution. This is our initial basic feasible solution. So in this case, there's only one entering variable, right? There's no choice, so we're going to pick x1 to be the entering variable. I'm going to look for the leaving variable. So I'm going to look at the minimum ratio test. Remember, so the ratio for row 1 is equal to 0, ratio for row 2 is equal to 0, and ratio for row 3 is equal to 1, right? So there are candidates for the leaving variable, right? So both x5 and x6 actually achieve the same minimum ratio. So which one am I going to pick? Well, I'm going to pick x5 because 5 is smaller than 6. Okay, so x5 has a smaller index than x6, so I'm going to pick x5 as the leaving variable. Is that clear? Okay, so in the first tableau, then x1 will enter and x5 will leave. And indeed, actually, that's what happens here. Okay, x1 enters and x5 leaves, and we obtain this tableau right here. So now, there are two candidates for the entering variable. Okay, there's x2 and x3 because both of them have negative coefficients. So which one am I going to pick according to Bland's rule? I'm going to pick x2, right? Why is that? Because once again, the index of x2, which is equal to 2, is smaller than x3. Okay? So now x2 enters the basis, okay? Or x2 becomes the entering variable. What about the leaving variable? Well, there's no ratio for row 1. Okay? For row 2, the ratio is equal to 0. For row 3, the ratio is equal to 1. And there's only one eligible leaving variable. So I'm going to leave that variable, which is x6, right? So x2 enters and x6 leaves. Which brings us to this solution. Is everyone following? Okay. All right, in this case, there's only one entering variable, which is x3. Okay, so I'm going to enter that variable. What about the leaving variable? Well, I'm going to look at the ratios again. So the ratio for row 1 is equal to 0. The ratio for row 2 is equal to 0. And the ratio for row 3, well, there's no ratio because there's a negative coefficient. So again, there's a tie. Okay. And the minimum ratio is achieved by x1 and x2. So which one am I going to choose? x1, right? So because of Bland's rule, I'm going to pick x1. So x3 enters and x1 leaves. Okay? Which brings us to the next solution. So here we have x3 as the basic variable and x1 becomes non-basic. Now, again, I have a choice for the entering variable. Okay, both x4 and x5 can be the entering variable. So which one am I going to pick? x4, because 4 is a smaller index than 5. Okay, so what's the leaving variable? Well, for row 1, there's no ratio. For row 2, the ratio is equal to 0. And for row 3, there's no ratio again. So there's only one eligible variable, which is x2. So x4 enters and x2 leaves, which is this solution right here. So far, we're still doing the same things, right? So nothing has changed. So here, there's only one entering variable. There's no choice. I'm going to enter that. For the leaving variable, I'm going to look at the ratio again. The ratio for row 1 is 0. The ratio for row 2 is 0. And there's no ratio for row 3, basically, right? So which one am I going to pick? Well, both x3 and x4 achieve the minimum ratio, and x3 is a smaller index, so x3 becomes a leaving variable. Okay? So which means that x5 enters and x3 leaves, which brings us to this solution. Okay, so we're still following the same steps. All right, so here, what are the potential variables to enter? I have x1 and x6. Okay? So by Bland's rule, I'm going to actually pick x1. Okay? Now, this is where you should be careful. So note that this is actually a larger negative value, right? Okay? So which means that if I try to increase x6, it seems like I'm going to get more benefit, basically, right? As opposed to x1. Okay? However, since this is a degenerate solution, I'm going to follow Bland's rule. So I'm going to ignore the fact that this one seems to be a better sort of entering variable. I'm going to ignore that, so I'm going to pick actually x1, okay, as my entering variable. This is important. Okay? And we only apply Bland's rule when the solution is degenerate. Okay? So if the solution was not degenerate, then I would simply pick x6 as the entering variable. Okay? So since we have a degenerate solution, because there are some basic variables which are 0, now I'm going to actually pick x1 as the entering variable. Okay? So in this case, there are two potential variables to enter. Both x1 and x6 can enter the basis. Okay? And in fact, it seems like entering x6 seems better because it has a negative, larger negative coefficient, basically. Okay? However, since this is a degenerate solution, I'm going to ignore that. I'm going to apply Bland's rule, and Bland's rule will tell me that I should pick x1 over x6, despite the fact that this one is more negative. Okay? So as a result, I'm going to ignore the fact that this one is more negative. I'm going to consider the fact that this is a degenerate basic feasible solution. So I'm going to pick x1 over x6 as the entering variable. Is that clear now? Okay? Well, if x1 enters, then what's the leaving variable? Well, what's the ratio for row 1? There's no ratio because there's a negative coefficient. What's the ratio for row 2? It's going to be 0. And ratio for row 3 will be equal to 1. So then which one will leave the basis? x4 will leave the basis. Now note that, unlike this one, now x1 enters and x4 leaves, right? So which means that my basic variables now will be x1, x5, and x7. x5, x1, and x7. Is that clear? All right, so let's look at the next solution. Well, that's exactly this solution right here. Okay? So now this is still a degenerate solution. The objective function still hasn't changed. Okay, all the variables are still the same. So there's only one entering variable, and I'm going to enter that. And for the leaving variable, well, there's no ratio for row 1. There's no ratio for row 2. But the ratio for row 3 is equal to 1. Okay? So which means that x3 enters and x7 leaves. And that will give me this solution right here. And this solution is actually optimal for my problem. Okay? So which means that if I apply Bland's rule, then I will never actually cycle with simplex method. Okay? So Bland's rule actually assures that, guarantees that the simplex method will never cycle. Is that clear? Okay? So as a result, despite the fact that, when there's degeneracy in the problem, there may be some complications. Fortunately, there's Bland's rule that sort of takes care of that. Okay? So whenever you have a degenerate LP problem, a degenerate simplex tableau, then you should always apply Bland's rule to make sure that you will not cycle. And if you apply this rule, then it guarantees that you will not come back to the same solution again. Okay? However, as we have seen in this example, if you don't apply this rule, if you pick the entering and leaving variables arbitrarily, then you may have a problem. Okay? Is that clear? So is this rule clear? All right, any questions? So once again, I mean, this should be, I sent this to you by email, so does everybody have a copy of this? All right. All right, so Let me just summarize the results. So this is theorem number 4. So it says that the simplex method never cycles and always terminates in a finite number of iterations. And by iterations, I mean simplex tableaus, basically. If Bland's rule is applied, in the presence of degeneracy. So basically, what this says is the following. So even if the problem is degenerate, even if the problem has degenerate basic feasible solutions, if you stick to Bland's rule, if you apply Bland's rule, then you're guaranteeing that the simplex method will never cycle and will always find either the optimal solution or detect that the problem is unbounded. Okay? So it will never get stuck, in other words. Any questions about that? So that's a good question. So the question is, even if the problem is not degenerate, even if the solution is not degenerate, should we still apply Bland's rule? The answer is no, actually. Okay, so if there's no degeneracy, then we know that simplex method never gets stuck. Okay, so this is only a sort of solution to the problem of not getting stuck, basically. Okay, so if you want to make sure that, and you can only get stuck if there's degeneracy. Okay, if there's no degeneracy, then you never get stuck. Okay, because remember, essentially we said that if the problem is not degenerate, then every basic variables correspond to a different corner point. So which means that every time I change my basic variables, I'm actually moving to a different solution. Okay? So this problem only happens when there's degeneracy. Okay? Other questions? So a quick note, Bland actually is, well, he was my professor when I was a PhD student, so he's still alive. He's a very nice guy, okay? A smart guy too. And his rule is still applied, okay? So, any questions? All right. So, now I think we're done with this. Any questions about this? I'm going to shut it down. So basically, whenever you have degeneracy, you should always apply Bland's rule. Yes, that's the answer, okay? All right, so now I can give you the outline of the simplex method. So given a maximization problem, I'm going to only describe it for maximization problem because we know how to convert a minimization problem into maximization, right? Just multiply the objective function by -1. So the first step is to convert it into standard form. Convert the LP into standard form. Okay? And we know how to do this, right? We know that every LP problem can be converted into standard form. The second step is find an initial basic feasible solution. The third step is, so there's an if condition. If there's a negative coefficient in row 0, you would enter that non-basic variable. So what's the second step? Then we should determine the leaving variable. So apply minimum ratio test to determine the leaving variable. To determine the leaving variable. let me just squeeze it here. So in 3C, if there's no leaving variable, then what do I conclude? So suppose that there's a negative coefficient in row 0, but there's no leaving variable. We've seen this before, so then the problem is unbounded, exactly. So then the LP problem is unbounded. Otherwise, pivot on the entry, under the entering variable, in the row corresponding to the leaving variable. And in 3D, we just go to 3 again. So if there's a negative coefficient in row 0, then we apply all of these steps, 3A, 3B, 3C, and 3D. And else, so else means if the condition in 3 is not satisfied, then we go to 4, which means that the current BFS is optimal. So basically, what I'm presenting you here is how you would, for example, code the simplex method if you wanted to sort of write a solver. I mean, this is the basic algorithm. So I give you a maximization problem, and you know how to convert it into a standard form, right, by adding slack or subtracting excess variables in some case. Then we find the initial basic feasible solution. And if there's a negative coefficient in row 0, then I'm going to enter that variable, because if I enter that variable, then I know that my z value will improve. Then I'm going to apply minimum ratio test to determine the leaving variable. If there's no leaving variable, then I stop and declare that the problem is unbounded. Otherwise, I'm going to pivot on the entry underneath the entering variable and in the row corresponding leaving variable. Then I go to 3 and repeat the steps. If there's no negative coefficient, then I actually arrive at this stage. Then the current BFS is optimal, and I stop. Okay? And this is precisely the algorithm that we've been using, actually, okay, in all of these examples that we have seen. Of course, if it was a minimization problem instead, then what part would change in this algorithm? Exactly. The only change would be, instead of looking for a negative coefficient, you would now look for a positive coefficient, basically, right? Okay. Apart from that, everything is the same. So as a result, essentially, this is the whole outline of the simplex method, okay? So this is how the algorithm works. Any questions about this? All right. So next, we're going to try to understand what the simplex method more closely. And we're going to discuss the simplex method in matrix notation. So let's consider an LP problem in standard form. Okay, consider an LP problem in standard form. So suppose that's a maximization problem. Okay, so I have C1x1 plus C2x2 all the way up to Cnxn. So this is my objective function. And since it's standard form, basically, I have equality constraints, which I'm going to abbreviate as AX equals B. So think of this as a system of equations, basically. So these are my equality constraints. And of course, I also want to make sure that x is greater than or equal to 0. So here, x is a vector. X greater than or equal to 0 basically means that each component of x is greater than or equal to 0. Okay, so for example, the vector x can contain 10 decision variables. So each of these variables should be greater than or equal to 0. So it's just a shorthand notation. Okay. So let me say that x greater than or equal to 0 basically means that x1 is greater than or equal to 0, x2 is greater than or equal to 0, all the way up to xn is greater than or equal to 0. Sorry? Okay. All right, so A is an m by n matrix. So it has m rows and n columns. Okay. X is an n-dimensional vector. And the right-hand side B is an m-dimensional vector. So essentially, I'm assuming that there are m equality constraints, right? So the number of rows of A is equal to m, and each row corresponds to an equality constraint, so there's a total of m equality constraints. And then what I'm going to do is I'm going to define a new sort of vector, which I'm going to call C, and C will be given by C1, C2, all the way up to Cn. So it's going to be a row vector, basically, okay? So, and its components will consist of the coefficients of the objective function, okay? So C, I mean, you can think of C as a 1 by n matrix, okay? It has one row and n columns, basically. All right, so with this definition, I can actually write this even in a shorter form, basically. So how can I express the objective function in terms of C and X? So remember, we're defining our X to be the vector of our decision variables. Okay. And what does the objective function look like? Well, I'm multiplying this vector by this vector, basically, right? So C1 times X1 plus C2 times X2 and so on and so forth. So how can I express that? C times X, exactly. So I can write this as maximize Cx subject to Ax equals B and X greater than or equal to 0. Did everybody follow this? So basically, I mean, think of this as the inner product of this vector and this vector, basically, right? That's my objective function. So C1 times X1 plus C2 times X2 and so on and so forth, but that's exactly the same as C inner product with X, basically, right? So this is just the dot product, right? Okay. So here is what I'm going to do. So we're going to try to understand what the simplex method does sort of more carefully, okay? So what exactly is it doing? What do those tableaus correspond to? And so on and so forth. So to do that, let xp and xn denote the vectors of basic and non-basic variables respectively. So similarly, let's B and N denote the columns of A, columns of matrix A corresponding to variables xp and xn respectively. So we have seen this before. We know how to sort of figure out the matrix B for a given choice of basic variables. Okay? All right, so my first question is the following. How many basic variables do we need for such a problem? What's the number of basic variables? This is something you should be able to say immediately. M, exactly. So we need the same number of variables as number of equations, basically, right? So as a result, xp you can think of it as a m-dimensional vector, okay, which consists of the m basic variables. Then how many variables am I going to have in xn? N minus m. So I'm going to simply subtract the number of basic variables from the number of all variables. Okay, so that's good. Now, what is the size of the matrix B? Well, remember, B consists of the columns of A underneath the basic variables. Okay, so how many rows will there be in B? That's same as A, right? So I'm not adding any new rows, so the number of rows is the same as M. What about number of columns? So I'm going to pick as many columns as the number of basic variables, and there are m basic variables. So as a result, this is just a square matrix exactly. And what's the size of n? How many rows does n have? How many rows? Again, it's equal to m. And number of columns is exactly equal to n minus m, right? So what I'm doing is I'm basically looking at my matrix A, and I'm picking m columns for B, and I'm picking m minus m columns for m, basically, right? And I'm not changing the rows. Since there are m rows, both B and n have exactly m rows. Okay? All right. Then what I'm going to do is the following. Similarly, I'm going to decompose the vector C. So let CB and CN denote the objective function coefficients corresponding to xp and xn, corresponding to basic and non-basic variables. Let me try to explain this. For example, suppose that the first variable is basic, the third variable is basic, and the fifth variable is basic, just as an example. So x1, x3, and x5 are basic variables. So then my CB will consist of C1, C3, and C5, basically, okay? So I'm going to just look at the coefficients of my basic variables. And then the rest, of course, will be the coefficients of non-basic variables, okay? So just like I decompose my matrix A, I divide it into two, I'm also dividing my C vector into two as well, okay? For CB, I'll just take the columns corresponding to my basic variables, and for CN, I'm going to take the columns corresponding to non-basic variables. Is that clear? All right, what are the dimensions of CB and CN? So how many coefficients will there be in the vector CB? There's going to be m of them, right? So as a result, CB will be a 1 by m vector, or m-dimensional row vector. What is the dimension of CN? So it's going to be an n minus m dimensional row vector, okay? It will consist of the coefficients of non-basic variables. Is that clear? So, all right. So now I'm going to rewrite my problem in the following way. So I'm going to maximize. Instead of C times X, I'm going to write it this way. CB times XB plus CN times XN. And I claim that this is the same thing as C times X. Okay? Why is that? Well, because essentially what I'm doing is, instead of writing the objective function that way, I'm first looking at the basic variables. Then I'm adding the non-basic part as well. Okay? So I'm just sort of changing the order if necessary. Okay? But I'm still adding up the same sort of terms. So as a result, I can write the objective function this way. Is everybody convinced that this is true? Okay? All right. Then I'm going to write my constraints in the following way. So instead of writing it as A times X is equal to B, I'm going to write it as B times XB plus N times XN is equal to B. Again, this is the same thing by the same reasoning. Okay. B times XB plus N times XN is exactly the same as A times X, basically, right? Okay. And then I'm going to have XB is greater than or equal to 0 and XN is greater than or equal to 0. So essentially all I'm doing is I'm just sort of decomposing my variables into basic and non-basic parts, okay? And that problem is the same as this problem, actually. Okay, so, which is the same as this problem. So far, I haven't done anything sort of extraordinary, okay? Now, since B is invertible, now why is B invertible, of course? Well, it's a square matrix, that's important, but not every square matrix is invertible, right? Exactly. So it comes from the definition of basic variables, right? In order for XP to be basic variables, the corresponding matrix P should be invertible, right? So that's how we define basic solutions. So since P is invertible, I can do the following. So what I'm going to do is I'm going to look at this system of equations, okay? And I can multiply this from the left by the inverse of B. Okay? So that's exactly what I'm going to do. I'm going to multiply both sides by B inverse. And this is what I have basically, right? So if you multiply both the left side and the right side by B inverse, this is what you have. All right, so I'm going to sort of work on this. So B inverse times B times XP, what do I get from the first part? Just XP itself. Okay. And what's the second component, second term? B inverse times N times Xn. And the right-hand side is the same as B inverse times B. Sorry?
B inverse times B is XP.
Well, okay, so the value of B inverse B will be XP. Okay, but right now I'm not assuming that Xn is equal to 0. So I'm just looking at this general system still, okay? So right now I'm not putting any values for XP and Xn. Okay? So essentially, this tells me how XP and Xn are related in general, right? Okay? So as a result, XP is always equal to B inverse B minus B inverse N times Xn. Okay? And for the basic variable, of course, this is going to be 0. And if this is 0, then I get simply B inverse B. But for any other solution, this should always be satisfied. Okay? Regardless of what your solution is. Because AX equals B is still equivalent to this equation, basically, right? Okay? Now, what's the point of this? Well, so now let me define my Z corresponding to the objective function. Okay? So now what I'm going to do is, instead of XP, I'm going to write this component here. Okay? I'm going to substitute this for XP. So which means that I have CB times B inverse B minus B inverse N times Xn plus Cn times Xn. Again, nothing magic so far, right? All I'm doing is substituting this for XP. Okay? All right, so now I'm going to work this out a little bit. So I have CB times B inverse times B for the first term, minus CB times B inverse times N times Xn plus Cn times Xn. Okay, simple algebra. All right. So then I'm going to write this CB times B inverse times B plus, I'm going to write it in this way, Cn minus CB B inverse N times Xn. Sorry. Times Xn. Can I do this? Well, so I still have Cn times Xn, okay, which is the same thing as this one. And I still have minus CB B inverse N times Xn, which is the same as this one, right? So I'm just factoring Xn out, basically, okay? Any questions so far? So, simple algebra, okay? So then what I'm going to do is I'm going to take this part and move over to the left, okay? And if I do this, I have to multiply this by minus 1. So I'm going to end up with the following. Z plus, now, CB B inverse N minus Cn times Xn is equal to CB times B inverse times B. Okay, so all I'm doing is I'm just sort of putting this on the left-hand side. And if I do that, I'm going to multiply this by minus 1. So I have CB B inverse N minus Cn, right? So this is exactly what I have. Okay. So now I'm going to put everything in the Tableau form. So I have my Z, I have my basic variables, I have my non-basic variables, and I have the right-hand side. So this is the equation corresponding to the objective function. Okay? So the coefficient of Z is equal to 1. Note that XP does not appear on the left-hand side. Okay, so which means that the coefficients of basic variables are 0. Okay? What are the coefficients of xn? Well, they're exactly given by this vector right here. So it's going to be CB times B inverse times n minus Cn. Okay? And what's the right-hand side value? CB times B inverse times little b. Okay? All I'm doing is I'm just sort of copying these coefficients into this Tableau form, right? One thing you should be careful about is that this is actually a vector, okay? There's a bunch of coefficients here, okay? There's more than one, because xn is also a vector, and xp is also a vector as well, okay? All right, then I'm going to look at this one right here. So the coefficients of z is equal to 0. Underneath xp, I just have the identity matrix, right? So I times xp plus b inverse times xn. Underneath xn, I have b inverse times n. Okay. I is the identity matrix. Mm-hmm.
Z eksi mi yazıyor, artı mı yazıyor? Parantezin önünden mi?
Z plus. Uh-huh. So essentially what I'm doing is I'm just sort of taking this and putting it on the left-hand side, right? Z is equal to this, which means that Z plus this is equal to CBB inverse B, right? Okay. All right, what's the right-hand side value? Right-hand side is just B inverse B.
In terms of identity, can you write one?
Say again?
Identity, in terms of identity, instead of identity, can you write?
Well, no, we cannot, because there are m variables here and there are m rows here, right? So essentially, if you think about this a little bit, well, this is just like the canonical form that we were doing with the simplex method, right? So remember, underneath each basic variable, we have the columns of the identity matrix, right? And this is exactly what we have here, okay? So essentially, this is exactly what the simplex method is doing, okay? So this is, the numbers that you see in this Tableau are given by all of these sort of expressions, okay? So this is important because, so therefore, therefore this is the simplex Tableau corresponding to the basic feasible solution xpxn. So which means that essentially, when we apply the simplex method, when we sort of compute these tableaus, we're just sort of doing these operations implicitly, okay? So of course, up to this point, chances are that you weren't aware of this, but essentially, the simplex method, all these numbers that appear in the tableaus, they have a certain meaning, basically, okay? They can be expressed in as certain expressions, and these are the expressions that we need, okay? So for example, the right-hand side value is always given by b inverse times little b, okay? The right-hand side of row 0 is always given by cb times b inverse times little b, and so on and so forth, okay? Now, what's the main message here? Well, basically, if I give you a bunch of basic variables and the corresponding non-basic variables, then you can immediately construct the simplex Tableau right away. Okay, this is important. Okay, so which means that for every basic feasible solution, you can construct the corresponding simplex Tableau right away using these expressions over here. Okay, so let me write that down. So therefore, given the original LP problem, the simplex Tableau corresponding to any basic feasible solution can be computed directly without using the steps of the simplex method. Now let me ask you a quick question. So why is this important? So Sorry?
Time saving.
So it can save time. That's good. Okay. So think of the following case. So suppose that you have a problem, okay, and you know that, well, you have an intuition, let's say, that, you know, these variables have to be basic in an optimal solution, okay? So for example, you look at the problem and you say that, you know, it seems to me that x1, x4, and x6 actually should be basic in an optimal solution, okay? Then what you can do is you can construct the simplex tableau immediately corresponding to the solution, okay? And since this assume that this is a maximization problem, well, these coefficients are 0 already. I'm going to look at the coefficients of non-basic variables, and if all of them are positive, basically, okay, then this is an optimal solution. So you can tell that that solution is optimal immediately by just constructing this tableau, okay? So which means that you don't need to do any steps of the simplex method. All you need to do is just sort of construct this tableau, and this tableau will tell you whether the solution is optimal or not right away. Is that clear? Okay. So that's important. So in the next class, what we're going to do is we're going to use this fact on an example to show that for a given LP problem, we can construct the simplex tableau corresponding to a basic feasible solution right away. Okay. So this gives us a chance to start at an advanced solution, if you like. Okay. So rather than starting with the worst possible solution, you can start with a better solution, if you can guess the basic and non-basic variables correctly, of course. Okay. Is that clear? All right. So I'll see you next time.